We've been talking about periodic trends in the periodic table. One of these trends is electron affinity. It's a little bit like the opposite of ionization energy. It's the energy change when a neutral atom in the gas state gains an electron. Ionization energy was a neutral atom in the gas state losing an electron. So we can write a chemical equation here, a generic metal, well, it's usually not a metal, but some element M, plus an electron gives us a -1 charge plus EA electron affinity. Okay. Electron affinity is usually negative, meaning that when you add an electron to an atom, it is releasing energy, but sometimes it's positive. Some alkaline earth metals and all of the noble gases have positive electron affinities, meaning they resist having an extra electron put on them. Why do you think the noble gases would not like an extra electron? It would make them less stable, yeah, because they've got their full valence shell, they've got 8 valence electrons, they're kind of like in that sweet spot. If you put another electron on them, they're not going to like that. The alkali metals and the alkaline earth metals aren't going to be big fans of that either, because that makes them move away from being stable. They would prefer to lose electrons. The trends in electron affinity are less regular than other trends. So these are really kind of vague. The best trend is that electron affinity decreases, becoming more positive as you go down group 1A. In other groups, we don't see a trend up and down like that. Electron affinity will generally become more negative. It will increase as we go across a period. That kind of makes sense because what kind of an ion does, like, fluorine want to be? Or what kind of an ion does it actually become? -1. So it forms a -1 ion, and so it makes sense that its electron affinity would be negative. So group 5A elements have lower electron affinities than expected because when you put that extra electron on there, it has to pair up with another one. And we see that groups 2A and 8A have very low electron affinities because the added electron goes into a higher energy level. So that's not very favorable. The highest electron affinity in any period is going to be the halogens, whichever halogen is in that period. Here's a table showing some electron affinities, and the trends are just not that great. If we go down group 1A, we see that the electron affinities become more positive. So it becomes less favorable. As we go across a period, we see that the most negative electron affinity is going to be in group 7A. All of the halogens have electron affinities that are greater than 1, so we don't even give them the number, it just says greater than 1. Properties of metals and nonmetals. There are trends in metallic character. So a brief review here. As the name suggests, a nonmetal is a not metal. It's sort of opposite. So we can look at these characteristics. Metals are malleable and ductile, meaning they can be hammered into sheets and drawn into wires. You hit a piece of metal with a large hammer and you can dent it, but it's not going to shatter. Nonmetals, in contrast, are brittle in the solid state, and they tend to shatter if you hit them with a hammer. Metals are shiny, lustrous, they'll reflect light. Nonmetals are the opposite. They are dull and non-reflective. Metals conduct heat and electricity. Nonmetals are insulators, both electrically and thermally. Metal oxides are basic and ionic. Nonmetal oxides are acidic and molecular. Metals form cations. Nonmetals form anions. Metals lose electrons. Nonmetals gain electrons. So they really are kind of opposite of each other. I find the metal characteristics easier to remember, and so then the nonmetal, it's like, well, what would be the opposite of that? So metallic character is how closely do an element's properties match up with the classic properties of a metal, ideal properties of a metal. This is, I think, is actually the easiest trend of all of them to figure out. Metallic character decreases as you go from left to right across the period, and it increases as you go down a column. And you can actually figure this out because we can tell by that stair-step line dividing the two sections of the periodic table that the nonmetals are in the upper right corner and the metals are in the lower left. So let's look at a periodic table. That's more helpful. So that stair-step line is right in here. So if we're following period 3 going across, over here on the right side, these are nonmetals, and on the left are metals. So it makes sense. Metallic character is decreasing as we go towards the nonmetals. As you go down a group, we're starting with nonmetals and going into the metals, so metallic character increases as we go down. In the middle on each side of this line are the semi-metals, and their characteristics are in between. Any questions? Another way of looking at it, as we go across, we're going from the metals through the semi-metals into the non-metals, metallic character decreasing. It doesn't help us much to look over here, but if we look at a trend at a group over here, we see we're going from non-metals to metals, and so that's the trend. So on the basis of periodic trends, choose the more metallic element from each pair if possible. Well, this is similar to some of the ones we've done. For the other trends, germanium or tin, we need to find those guys on the periodic table and see where they are in relation to each other. So there's germanium, there's tin. Which is more metallic? Tin, the one on the bottom. How about gallium or tin? So now we're looking at diagonal. The trends going across become less metallic, going down become more metallic. So here the trends are opposing each other. If we find these on the periodic table, we see that they are both metals. So I would say not possible. We can't really tell. How about phosphorus or bismuth? So phosphorus is up there, bismuth is down here in the same group. Bismuth. That one, you don't even need a trend because phosphorus is a nonmetal, bismuth is a metal, right? So hopefully bismuth is more metallic. Boron or nitrogen. So here we've got this. Who's more metallic? Boron. Neither of them are metals, but they are more metallic. Okay. Just like, well, I won't go there. You get it.